Alright, what we're going to be doing today is partly a continuation on what we did last time. And the last time we actually talked about alkyl halides, and that's like substitution mechanism, substitution and elimination reactions in alkyl halides. So right now we're going to be focusing on aryl halides. That's just like a continuation on that. But aryl halides have like a completely different characteristic from alkyl halides, so I'm taking it as a topic on its own. But aryl halides are also known as aromatic halides because they are benzene or an benzene is not really an aromatic compound, but it's the most common one. So let me just use it. They're like benzene derived compounds or aromatically derived compounds, aromatically derived halides. That's just basically what they are. So let's just go on and see what we can do today. Now, what are aryl halides? That's the first thing we're talking about. Now, what are aryl halides? Now, like I said earlier on, they are aromatically derived halides. So basically, aryl halides are halogen substituted aromatic compounds. So it's still kind of like the same thing, just in a different word. They are halogenated or halogen substituted aromatic compounds. That means they are formed when a halogen, let's call it that halogen X, substitutes a hydrogen in an aromatic compound, for example, benzene. Oh, let's just erase everything. Now, let's just say now the aromatic compound X substitutes. Okay, let's get another page. I'm just trying to do this. Now, the hydrogen or the halogen, that's the X, it substitutes a hydrogen present in benzene. Let's say the hydrogen here. The halogen actually comes and substitutes the hydrogen, and it ends up leading to a formation of compound like this, X. So let's just draw the circle, show that it's actually an aromatic compound. So this is just basically what aryl halides are. That's like from what I've been saying earlier on, they are benzene, they are substituted like compound halogenated or halogen substituted aromatic compound. So that's basically what they are. So let's just go on and see how far we can go. So I need to go back and talk about what I was saying earlier on. Now they are formed when halogen substitutes a hydrogen atom in an aromatic ring or compound. That means when a halogen, like I showed you, when a halogen substitutes a hydrogen in an aromatic ring or compound. Now in aryl halides, the halogen is attached to an sp2 hybridized carbon. Now, we all know that sp2 hybridized carbon is actually found in double bonds and whatever. And we know from our structure of benzene. So let me remove this and actually illustrate that. We know from our structure of benzene. Benzene is just a ring of like this double bond are in resonance. That means they are constantly changing their position. That means the carbons present here, let's bring this out. This is carbon 1, this is carbon 2, whatever. They have like, they are doubly bonded, or should I say, they have a double bond. That's just what I'm just trying to say. And we know that double bond, like, or double bonded carbon are formed when an s orbital mixed with two p orbital, that's the px and the py, and that leads to the formation of sp2 hybridization, and that's what gives us a double bond. So now, like I said earlier on, the halogen is attached to an sp2 hybridized carbon. That will lead to like a variation from everything we've been talking about in alkyl halides earlier on. So let's just see now. In aryl halides, the halogen is attached to an sp2 hybridized carbon, unlike alkyl halides in which the halogen is attached to an sp3 hybridized carbon. Hence, this leads to a variation in character and reactivity because the halogen is attached to an sp2 hybridized carbon. Just like how alkanes and alkanes have different characteristics, they won't undergo the same reaction. Hence, and that's the same way um, an aryl halide won't undergo the same reaction with an alkyl halide. So that's basically the illustration. So let's go over to the next point. Now, aryl halides are less reactive towards nucleophilic reagents when compared to the reactivity of alkyl halides with those reagents. So with those nucleophilic reagents, aryl halides are less reactive. They are less prone to undergo maybe another substitution, or they're less prone to undergo substitution reaction when compared to alkyl halides. Alkyl halides could undergo substitution reaction easily, and that's like a major variation in their character compared to that of alkyl halide, because it's actually showing us that the reactivity, we don't expect an aryl halide to react the same way with an alkyl halide, or with the same reagent, or at the same condition. In a way, just like remind yourself of benzene. Now, benzene is more stable compared to other like alkyl groups or whatever, alkenes and whatever. Why is benzene so stable? Because of the resonance structure, and I'll actually talk about that later on. That's kind of like the same reason for aryl halide. It's basically because of that resonance structure, and that's just, I'll just talk about that later on. So let's just go on. Now, the reason for this decrease in reactivity can be found in 2 points. Number one, the aromatic nature of benzene, like I was saying earlier on, and the possibility for resonance in aryl halides. Now, this aryl halide like possibility for resonance is kind of different from that of benzene. I'll actually show you what I'm talking about here in the possibility for resonance in aryl halides. I'll actually talk about it and show you what I'm actually talking about. So let's just go on and just see how far we can go. Now, the next slide, the aromatic nature of benzene. That's the first thing we're going to be talking about. The aromatic nature of benzene. Now, in benzene, each carbon ring is sp2 hybridized, unlike that of alkyl halides, which are sp3 hybridized. So now, it's just something that I'm sure you all know what I'm trying to talk about now. In benzene, the carbon ring, I've showed you the structure earlier on. The carbon ring in benzene is sp2 hybridized, but that in aryl, but that in alkyl groups, they are either sp3. Let's just say we're talking about like, yeah, they are they're sp3 hybridized. That's the carbon that we're actually talking about now, and we know that the sp2 hybridization leads to the production of a shorter and stronger bond when compared to that of the sp3. Hence the carbon halogen bond in aryl halide requires more energy to break when compared to that of alkyl halide, and hence can be said to be more stable than an alkyl halide. So what this point is just trying to talk about is that the double bond is shorter. Let me just make that better. Double bond is a shorter bond compared to the single bond. And the double bond is a stronger bond because you're actually breaking two bonds, not breaking one. So we expect the double bond to be a stronger and a shorter bond. And for a reaction to occur, bond breaking and bond formation must occur. But since the like carbons are sp2 hybridized in benzene compounds and whatever, we expect it to be more stable and hence require what, more energy for it to actually break that bond. And that's just what this point is just talking about. So let's just go on and see. Now, this also reduces the ease of ionization, hence they cannot undergo SN1 substitution. Now, remember when we're talking about substitution in alkyl halides or substitution here, let's just say organic halides in general because everything. So now, in SN1 reaction, I told you that a stable carbocation must be formed, and that's why tertiary alkyl halides easily undergo SN1 reaction because they always form a stable carbocation compared to that of um compared to like a primary alkyl halide. A primary alkyl halide does not form a stable carbocation, hence it undergoes by SN2 reaction. But now, because of this stability, they don't like the ease of ionization, like is not there. Like it reduces their ease of ionization and hence they cannot form ions at all. So SN1 reaction cannot occur. Now SN2 substitution is also not possible because the carbon in the aromatic structure, the aromatic compound, do not have a permanent position and hence aryl halides cannot undergo a backside attack, which is a characteristic reaction of SN2. So let me just show you what I'm talking about here. Now remember, okay, let's use a primary or let's just use. Remember when I was saying, if you can watch the last video, I'm sure you understand it better. Like, let's look at a primary alkyl. Like, let's just look at something simple. Let's look at ethyl chloride. So we have something like CC, and with let's say this was C or this our H. and our H, and our H, and H, and H. Now, so let's think of something. Now let's imagine our attacking nucleophile is hydroxide. So at the right conditions, hydroxide OH minus is coming to attack. Now, what do we expect to happen? As the hydroxide is actually, I told you a transition state is formed. If you can watch the last video, you understand what I'm talking about here. I'm just trying to summarize it. A transition state is formed where, as the chloride ion is leaving, the hydroxide doesn't attack the chloride ion. It actually comes and attack this hydrogen ion, this hydrogen atom. So at the end of the day, as this chloride ion is leaving like this, we expect what? The hydroxide ion to actually come in here, OH. So we can actually just remove the OH from here, so you won't get confused. OH minus. So that's what we expect, the hydroxide ion to actually be coming here to be attacking. I can see it's like attacking in an opposite side to where the chloride ion is living. And that's what I was trying to talk about, the backside reaction. That means wherever it's attacking, it always attacks where at the opposite side, at the opposite end of where the halide ion is living. If the halide ion was living from this position, it's come and attack. Yeah. Just at the opposite end. That's what it actually does. He attacks at the opposite end. And that's basically what I was just trying to illustrate. Now for benzene. Remember when you were talking about benzene structure? You can't really, I can call here my position 1, another person can call here his position 1. Benzene doesn't have like a permanent position 1, 2, 3, 4, 5, 6. Anywhere can be its position 1. Mainly the position 1 is depending on whatever subsequent group is really attached to it. But now for like alkyl halides, it doesn't like really have like a natural position 1, and hence a backside reaction cannot occur. That's the first reason why SN2 can't on like it can't undergo SN2. But let's say it crosses that boundary and the backside reaction actually occur. Now, look at it like the other point. Also for SN2, if by any means the nucleophile attaches itself to an aryl group, it will lead to the destruction of the double bond, and this will decrease the stability of the compound, leading to the formation of an alkyl, like an alkyl compound, or what should I say, a saturated compound. That's a better word, a saturated compound. Now, just like how benzene always undergoes substitution reaction, benzene can undergo elimination reaction and lead to function of like it's such. I mean, benzene can actually undergo like and lead to function like a saturated compound, but it doesn't do that. Why don't benzene undergo like elimination compound lead to function of a saturated compound? Even if it does, okay, let me just like before I get to that point, let me just explain. Benzene can undergo elimination reaction if the conditions are right. That's at high temperature, high pressure, all those mad conditions. But on a normal day, it won't undergo it. No, it won't. Why? Because the double bond, like I told you, benzene is one of the most stable compounds in organic chemistry. It's one of the most stable organic compounds because of that resonance effect. So benzene will rather undergo that resonance effect than to lose that double bond and form a saturated compound which is less stable. Remember, everything in chemistry, all elements, compounds, or whatever, their main aim is to attain stability, octet or duplex structure, and whatever form of stability, their main aim is to attain stability. So do you expect benzene to actually go for a less stable compound or a more stable compound? So it's actually go for a more stable compound, and that's why SN2 it can't really undergo SN2 reaction like substitution nucleophilic bimolecular. It can't really undergo it. That's the forming of SN2. So that's just what I was just trying to explain. So now the possibility for resonance. This is another condition. I remember I gave you two conditions. That's number one, aromaticity of benzene and whatever, and now or resonance effect of benzene. Now, second one is the possibility of resonance. I told you that the reason why some people might actually get this confused, like this condition is quite different from the previous one. Yes, benzene undergoes resonance and whatever, but aryl halide has its own like resonance effect that I'm actually just going to explain now. It's quite different. It's not just because of the benzene structure alone. The halide also plays a role. That is the halide ion. It also plays a role in this resonance effect. And I'll just like explain it now. Now, resonance can occur in aryl halides. Let me just read. This is because the halogen atom attached to the aryl group has 3 lone pairs of electrons. Hence, one of those lone pairs of electrons can be shared with the aromatic ring carbon and hence lead to the formation of a of resonating aryl halide. Now, if I ask you like to draw the dots, okay, the dot structure of chlorine, how will you actually just draw it? It's actually going to be like this: one electron, two electron. Okay, let me just draw it accordingly. So that's Cl. You first draw a single first, then you start going double. At the end of the day, what happens now? This lone pair, like this electron, can actually like bind to another electron there and create a function of a bond. So instead of us to just use this dot, let's just represent this by a line. So now just look at the other parts of benzene. I mean the other parts of this chloride ion. Or I'm using chloride ion for my example. These are lone pairs of electron. It has one, it has two, and it has three lone pairs of electron. Remember, to form a bond, you need how many electrons? Two electrons make a bond. So these two electrons can actually make a bond. Now, it already has a single bond here, like this single bond. This single bond is already present. So let me use a different color and call that single bond 1. Let's use red. Now, we call this single bond 1. Now, I told you how many electrons make a bond, like two electrons make a bond. So now these other electrons, these two electrons, let's say these two electrons now, these two electrons can actually come and form a bond here again, and they form the second bond. At the end of the day, this second bond can actually be going into the benzene and be leading to information what's resonance or a conjugated compound. Let me just use that word. Now it can actually be going and lead to function of resonance. At the end of the day, not only the benzene ion or like the benzene group actually participating in resonance will also be participating. The chloride ion will also be using its lone pair to participate in this resonance structure. I mean this resonance. At the end of the day, it also increases stability. It also increases stability because the chloride ion has the electron to give. So at the end of the day, it keeps giving that electron, and at the end of the day, like it will increase the stability of benzene because resonance effect also increases stability. So it end up increasing the stability of benzene, and this can also end up preventing nucleophilic substitution in benzene because of there are a lot of electrons. So nucleophilic substitution in benzene won't be like as high as it was before. So let me just try and draw some resonance structure of this. Let me just try and draw them. So now let's say this is our first one. Let me just draw two structures. And we say it's in resonance with this. So the first one, let's draw chloride. Now these are the two electrons of the chloride that are participating in the bond. Or let me just make that a little bit clear. Let me make everything big, a little bit big, and yeah. So let's go again. This is the Cl, and these are the two electrons. This is the first, and this is the second. Now I told you these two electrons actually go. I'll show you that later on. Now this is the benzene. This is the first like resonance structure. Then these two electrons, like I told you, they can actually like go into the benzene ring and actually increase the stability. And then the day, this will have a positive charge, and the two electrons will actually come. Let me put them like in a bracket. They actually come here, and the benzene, because of resonance, it like keeps moving. So let's just take something like this. Or let me just use that same structure. So let me take this off a little and make everything look like well arranged. So take this too. Start with here, then yeah, then yeah. Then at the end of the day, we end up having something like this. And you can see this structure continues because this bond, it will keep coming and going. And at the end of the day, if this like bond moves, let's say it moves, and let's take it out from here and say it moves. It's actually move like this double bond, it's actually like move to this position. I mean, it's a negative charge, not a positive charge. So it's actually moved to this position, and it will keep moving, and just like how resonance occurs. That's just I was just trying to explain it. So like you can see how resonance really like kind of like affects the stability because of this resonance. Like the benzene group, I mean the aryl group or the aryl halide is more stable And at the end of the day, reactions for something to be like more stable and whatever, it requires a high like energy to actually break that bond. And at the end of the day, it's like the reactions there, it's not going to be as much as that of an alkyl halide. So that's basically it. So now let me look at the next point. Now this shows that the carbon halogen group is not purely a single bond, but rather a partially double bond. A partially double bond. That's just what it's just trying to show. I'm trying to say that, and four electrons are being shared between, like four electrons are being shared between the halogen and the carbon group, because at the end of the day, after the resonance, it can keep drawing the resonance structure. If you know how to draw it, you can keep drawing. If you don't know, you can learn. Because of time, let me just try and run this up. Now, at the end of the day, let me just try and illustrate what I'm just trying to say. The Cl can actually come here with the C, and okay, let me take it. Let me just show you this. Now, let's say this is Cl. To end up having like with this carbon, because of after resonating like that double bond, you agree with me, double bond resonates, it's come here, 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 then to go back here, then to come back here, then to come back here. That's the way to be resonating that bond. So let's me erase like all these other inks so we can actually focus on what we're doing. At the end of the day, you can see the way, oosh, oh sorry. At the end of the day, you can end up seeing that the bond between the carbon, this carbon here, and the chloride, and like the chloride or whatever halide is there, I tell you two electrons make up one bond. Now we can see two bonds present. How many electrons will be present? Four electrons. And what would that do? That will end up increasing the stability of the bond. To end up increasing the stability of the bond, and it cannot like really be susceptible to like nucleophilic attacks because it has a lot of electrons. What does it need again? So what's it can actually be susceptible to electrophilic attacks. That's electron loving groups attack, but not nucleophilic attack because it's more like electron rich than electron deficient. So nucleophilic attacks actually reduce and electrophilic attacks actually increases. At the end of the day, benzene can actually undergo electrophilic like electrophilic reactions. So I might actually give some electrophilic reactions later on. Or let me just I'll give them later on. Let's just say. Now, note, everything we just discussed earlier applies to do not apply to benzyl halides. This is because its halogen is not directly attached to the aromatic group, but the CH2 group, which is sp3 hybridized, not sp2, and hence benzene halides behave like an alkyl halide and undergoes SN1 substitution reaction because they form a stable carbocation. So let me just talk about that point. Now, what is benzene halide? Benzene halide is actually like um when like this bond has now like kind of like been replaced with a CH2. The hydrogen you have been replaced with like a CH2 group, and this is like benzyl halide. So let's just obey and just draw a circle and whatever, just show that it's in resonance and whatever. So now, this benzyl halide, because the halogen will actually displace, for it to become a benzyl halide, it means the halogen actually have to displace one of this hydrogen. And it won't affect or it won't displace anything relating to the structure. It's only going to displace one hydrogen. And at the end of the day, bond here. Now, every carbon here, that's this carbon, this carbon, this carbon, this carbon, this carbon, they are all, and also this carbon, there's carbon here, they are all sp2 hybridized. But this carbon here is not sp2 hybridized. If you look at its structure, there's no double bond anywhere. It's not sp2 hybridized. Instead, it is sp3 hybridized. So this is called benzyl halide or whatever. So we don't expect this to undergo like or to have the characteristics or like the special characteristics of aryl halide because it's not an aryl halide, it's a benzyl halide. It's completely different from an aryl halide. So this benzyl halide actually is less stable than, or it actually is stable, or let me just say it's actually stable, but it's actually more prone to nucleophilic attacks when compared, like whenever you're comparing it to like a normal stable aryl halide. So look at the next point of what I'm just trying to say. They are even more reactive than aryl halides when like nucleophilic substitution. They are even more reactive than aryl halides because of the benzyl carbocation is very stable. And because of this stability, it actually undergoes SN1 reaction because the benzyl carbocation is more stable, like it's one of the most stable carbocations. And then at the end of the day, because of this sp3 and whatever, it's not really affecting like the resonance structure, so they are more susceptible to nucleophilic substitution. While that of an aryl halide is not really undergo nucleophilic substitution. So now, last thing I'm actually going to talking about is electrophilic substitution in aryl halides. Like I told you, I'll come back to it. Tangle actually came back to it because it's actually here. Now, aryl halides can undergo electrophilic substitution. That is, electrophiles can actually substitute a hydrogen present in the aryl halide. Now, this halogen present in the aryl halide actually determines the position of the carbon. Actually determines the position of the carbon. Because remember, I told you earlier on that in a benzene compound, or what should I say, an aromatic compound, the position one can be anywhere. So it's actually the group or a substituent group attached to it, like the most powerful or the most like authoritative substituent group attached to it, that actually determines where the position actually starts from. And the position and the most like because this is an aryl halide, so what do you expect that substituent group to be? The halogen group. So it actually determines the position to which the electrophile is attached to, and it's said to have like that is actually called like a directive influence. That's what it's actually called. Now remember, I don't know if you can remember, I told you earlier when we were dealing with benzenes that, or let me just take it as if I've not told you. Now, halogens are the activating group. We all know that halogens are the activating group, but they are actually auto and para directing groups. That is, auto is the second position and para is the fourth position. So they're actually auto and para um, auto and para directing group. And mainly this is because they have a lone pair of electron. Like I told you, they have halogens have lone pairs of electron. Now there's something like I found out that double bonded, like, or what should I say, substituent that have double bonded like compounds that are actually deactivating, they are meta directing. But when there's no double bond present and they have lone pairs, they're actually auto and para directing. So halogens are auto and para directing, hence attacking, like I'm just reading the last one. Hence, attacking electrophiles are directed towards the 2 and the 4 position, with the halogen determining the position 1. Wherever the halogen is present, that will be the position 1. Then the second position and the fourth position, that's where the attacking electrophile are actually directed to. So let me just give some examples. So now let's look at the nitration of chlorobenzene. Let's use chlorobenzene. Now the nitration of chlorobenzene. Now, this is our chlorobenzene Cl. Now, for nitration, we know we need H2SO4, and let me just put it on that so I don't take a lot of space, and HNO3, and heat is applied, so heat. At the end of the day, we end up having two compounds. So let me even go to the next page because I'm not sure this page could actually contain everything. At the end of the day, we end up having two compounds. These are first, and these are second. I tell you, it will actually lead to a function of like an auto and a para directing compound. Now, the first one is like the auto directing compound. It just depends. Whichever one is more stable, that one will be more dominant. Whichever is less stable, less dominant, and so on. But let's just leave that part for now. So now these are auto directing, and same thing. These are Cl, and these are position one. 1, 2, 3. These are fourth position, and this is our per directing. So at the end of the day, you can see that in the nitration of chlorobenzene, it's actually a function of two compounds, and because of the chlorine or the halogen is present there, it's actually leads to formation of what compounds. Electrophiles which are present in the auto and the pro direction. They won't actually go to any position of their choosing. It's because of this directing, like the directing group, that's actually the chloro group in this case now, to actually position them in the auto and the pro direction. So now let's take another example. Let's just take alkylation of bromobenzene. So I'm just erase this and just try alkylation of bromobenzene. Bromobenzene is still like chlorobenzene. It's just substituted with Br. Now the alkyl group. This Fiddlecraft. Yeah. Now in the presence of, sorry, Fiddlecraft alkylation, you can check it. That's the name of this reaction. In the presence of AlCl3 and heat. Yeah. Now I told you it's what you expect. It's going to actually take the alkyl group, or in this case the methyl group, and direct it in what direction? That's the ortho and the para direction. I've actually talked about Friedel-Crafts reactions. So if you want to actually know about their mechanisms, you can actually go back and just check it. Actually describe the mechanism on how Friedel-Crafts reaction actually occurs. So you can just maybe go back to the previous video and just check it out. So let's just go on. So at the end of the day, we end up having these are BR. So let me put a plus here. These are CH3, the methyl group. That's in the ortho direction. Oh, sorry. And this is in um the para direction. Now note if the okay, let me just change the position now so you won't get confused. Now let's say the bromine group. Let me remove that. Now let's say the bromine group now is actually okay. Let me erase this first structure. This is just an example. It's not really important. I just want to not to get familiar with one particular position, like this position for para. That's not true. That's not the main position from para. Like para can take any position. Let's just say now our bromine group is yeah, Br. So let's now look at the pro directing. We actually have to take from this now our position 1, 2, 3, and 4. And this is where our methyl group actually come and take place. Now we can also take it from position 1, 2, 3, and 4 and still have this. We can also go here and go here. Either way, that's correct. So that's just basically it. So now that's all for today. That's all I'll be taking for today. I don't know, we might actually be talking about vinyl and allyl halides. They are just kind of like really similar to this because of the undergo resonance, but there's just like a slight deviation for allyl halides. I think that's what we'll be talking about next time. So that's it for today. So thank you for watching. See you next time. You can subscribe to my channel for more of these videos, and you can like this video if it actually helped you. But if it didn't help you, you can actually go to like the comment box and actually tell me what you found, or tell me whatever you're finding hard so I can actually just explain to you. So thank you for watching. Goodbye.